Section 8.3 is springs and Hooke's law. So you guys actually saw a little bit of this back in Algebra 2 when you did the project that had the springs and you had to measure how much the spring deflected as you added weights. You saw a little bit of this law that you're going to see today. So forces and torques will stretch, compress, or deform an object. It doesn't matter if it's a spring or not, okay? If you do anything to any object, it's going to apply some sort of stress on the object, and that will cause a stretch, compress, or deformation on the object. This is easiest to see in a rubber band or a spring. So, if we stretch a rubber band, there's a force that tries to pull the rubber band back to equilibrium. So, try to picture that. And the equilibrium in this case is the unstretched length. So, as it's just sitting there resting. This is called a restoring force. So this vocab here is important. The restoring force is what brings it back to where it wants to be without any sort of force applied to it. So systems that exhibit the restoring forces are called elastic. So as long as we have a restoring force, we want to be able to come back to where we were in the first place, then we are in an elastic system. So basic examples of elasticity are rubber bands, springs. Those things want to come back to where they naturally were in the first place. Slinkies want to come back to where they were in the first place, usually. If you stretch a spring, a tension-like force pulls it back. If you compress a spring, it will try to re-expand to where it was in the first place. So those are elastic systems.
So do shocks fall underneath that?
Shocks. Shocks are basically springs, no matter what kind of shock you have.
Even if it's hydraulic?
Even hydraulics are basically like a spring. Yeah. Okay. Basically. So elasticity and restoring forces exist in stiffer systems as well. Steel beams bend in bridges as you roll across them. Bridges bend. Tables bend as you stand on them. Okay. So all of those things are exhibiting some type of elasticity. Even though it doesn't look like a spring, it actually is acting like one. They restore themselves to equilibrium after you pass by. Your leg bones flex as you apply a stress to them. And so they're flexing like each step you take. How hard a spring pulls back depends on how much you stretch it or compress it. The spring force always points opposite the displacement from equilibrium. Okay? So basically, what I'm saying here is literally everything up to a point can be modeled as a spring. Okay? So that's what we're going to do.
So like even this solid piece of table, if I stand on it,
Even a table
like
can
even
be
though
modeled.
It doesn't move.
It is moving. It is bending under your weight,
but it's just
and it will restore. It just doesn't bend to a point where you can see it. Usually, if you start to really apply a ton of weight to it, you will start to see it bend. If you remove the weight, it will come back, unless you bend it so much that it doesn't come back. So picture the slinky, right? Everybody usually had a slinky, and then usually it lasts for a little while until finally you stretch it too much, and then it doesn't come back, right? Now it's deformed. So that's where you stretched it too much, and now it's kind of toast. Like a bridge, you put too much weight on the bridge, and now the bridge is deformed. It's not going to come back. Okay. So in the picture, we have in like A here, we have the relaxed spring. So that is our equilibrium length right here. That's where the spring wants to naturally be. We compress the spring, so we're pushing it into the wall. We gave it a delta X. So we have this delta X right here. The restorative force is pointed in the opposite direction of the deflection. So that means it is pointed opposite of the deflection, so it's pointed outward. Okay, the spring force is pointed outward. If we stretch the spring, so we have a delta X now opposite that, so we're pulling it away from the wall, then the spring force is pointed opposite the deflection, which means it's pointed into the wall. So in B now, we have the equilibrium length again. We have our relaxed spring. We pull the spring out from the wall, so the spring force is pointed towards the wall. We pull our delta X out farther. That means that the spring force is just getting longer, but it's still pointed towards the wall.
So I'm assuming Hooke's law relates to like the farther out Olsen.
Yeah, we haven't gotten Hooke's law yet, but it will relate to the amount of deflection.
So could heat like change the elasticity of something?
Heat does change. Yes, exactly. Good question.
Is that gonna be something we learn about?
No. Okay, so now in C, the magnitude of the restoring force, this is important, is proportional to the displacement of the spring force from equilibrium. So here on the x-axis, we have our delta x. Here on the vertical axis, we have the force of the spring, and we can see the slope. Here, we have a linear situation. The slope is k as some sort of constant, and we have, in this case, 3.5 newtons per meter. So we have a linear relationship here, a proportional relationship. The amount of deflection I have is going to cause the amount of force that I'm pulling by to increase in a linear way. Okay? So the spring force then is some constant times delta x. We just don't know what that constant is.
Oh.
So, like I was saying, it's a linear relationship. The slope of the line k is the proportionality constant. We'll figure out what k is in a little bit. The value k depends on the spring. So if the material of the spring or the thickness of the spring, the gauge of the spring, it changes, then k is going to change. We call k the spring constant. And it has units newtons per meter. If k is large, the spring is stiff. If k is small, then the spring is relatively more floppy, like a slinky.
A table would be a very stiff spring.
A table, if we call it acts like a spring, then we would have a very stiff k value. Okay, so it'd be a very large k
But
value.
like a slinky would have.
Slinky would be very sloppy. Yeah,
So what's
slinkies
considered a
are
large
very
K
loose. So it'd be very small. What?
Was considered a large K value.
We'll do some problems and find out. Okay, so let's take a look at this one. The end of a spring is pulled to the right by 4 centimeters. The restoring force is 8 newtons to the left. So remember, we pulled it to the right. So here's equilibrium. We pulled it this way. So that means the restoring force is going to be pointed to the left. It wants to pull it back to equilibrium. Given the relationship shown in the figure that we saw before, if the spring is returned to equilibrium and then pushed to the left by 2 centimeters, the restoring force would be what?
As well.
All right, it is B. Why is it B?
Because
Because
it's
it's
a
proportional.
Proportional.
Directly
So
proportional.
4 divided by 8 is equal to 1/2.
And 1/2 times 4 is 2.
Right. Remember the units of K. It's newtons per meter, right? So if we pulled it 4 centimeters to the right, and that was 8 newtons, then we're getting 8 newtons per 4 centimeters, which would reduce down to 2 newtons per 1 centimeter. So now if we push it to the left
2 centimeters.
2 centimeters, then all we got to do is convert this fraction, and it will be 4 newtons per 2 centimeters. So the answer is 4 newtons. The other way, though, so it's 4 newtons to the right. So that's how you do it, okay? Very straightforward with proportional things. Okay, so Hooke's law now. The name of the section is Hooke's law, basically. So Hooke's law states basically what we just discussed, but it puts the relationship into a component form. So the negative sign indicates the restoring force and the displacement, remember, are in opposite directions. So we displace to the left, the restoring force is to the right. We displace to the right, the restoring force is to the left, or whatever direction it happens to be. The restoring force is just opposite that direction. So the x component of the restoring force of the spring here, force of the spring in the x direction. The negative sign just means opposite that. And then we have our spring constant is K, whatever that spring constant happens to be, and then times the delta X. That's it. Okay.
It's newtons divided by meters, and delta X is meters.
Yeah.
The meters on top and the meters form a
So then we
fancy
get just newtons left over. So we have, remember, the proportional relationship sitting over here that we were talking about earlier. And remember, the negative sign is just telling you we're opposite the direction of whatever the force applied is. So if the force applied is to the left, it would be a negative force. So we'd have a negative over here on the F spring. And then this negative sign over here would be positive. Okay? So the negative sign would just move to the other side. So in the y direction, Hooke's law is basically the same thing. The force of the spring in the y direction is negative, and then K delta y, just to indicate that we're going in the opposite direction. So this is not really a law like Newton's law. It works very well for some springs, but not for other springs. It's going to fail when the spring is stretched or compressed too far. Like when you take your slinky past the limit, the spring fails.
So what is that limit called? What's the name for that?
Well, we're going to get into that. So yeah, I know. So once you stretch something too far, it goes past its limit, then it basically is broken and it won't come back. So the whatever it is that you're dealing with, a spring, the table, the bridge, whatever, it's failed and it's toast.
So-
It's going to break.
Does
Okay.
that depend on the length of the spring?
Well, it could depend. It could be the material. It could be the length. It could be the thickness of it. Whatever. These things have their breaking point, and you just stretched it too far. You overloaded it, and it's done now. You can't come back. Okay. So we're going to use massless springs, quote unquote massless springs,
If only that
kind of like with our ideal pulleys. Okay. Which is a good approximation when the mass attached to the spring is much bigger than the spring itself, which is what we're going to be dealing with in this class anyway. So we don't have to worry about the difference there. So good with this?
Yeah.
Okay. So now several companies manufacture running shoes that have the thick heel pads containing springs. They actually do have springs to launch the runner back into the air after a heel strike. So when a 70 kilogram runner, so times 2.2 would be 140 plus another half of 70, so or a fifth of 70, 140 plus a little bit,
155 pounds.
maybe, yep. Rocks back on his heels so that all of his weight is supported by the heel springs. The springs compress by 1.2 millimeters. When he's running hard and hits the ground on one heel, the force compressing the spring is 5 times his weight.
Dang.
So the first question is, what is the spring constant K of a heel spring, and by how much do the springs compress during the heel strike when he's running? Okay, so we can do these, no problem. First thing I'm going to do is try to, like, maybe I'll draw a picture and try to visualize what's going on here. So we have an amazing foot.
Oh man.
Oh,
Dude, that's some
How
crusty
many
toes.
toes?
you know, when you're a runner, your feet get pretty messed up. So that's what that looks like. And then we have the spring on the heel. Looks pretty good.
Built into his feet. Dude.
Just, you know, if you guys do track, that's pretty much what's going on right there.
Spring shoes.
Okay, so now free body diagram on the heel. We got the heel, and then we have,
Weight down.
okay, so in the problem it said when a 70 kilogram runner rocks back on his heels,
So that means all his weight's gonna be concentrated.
all his weight is on one heel.
It's on 2, so it's divided by 2.
It's actually on 2 heels. So this is for the free body diagram for this foot. This is going to be 1/2 of the weight. Now up, what do we have?
You're gonna have the spring force.
Spring force, F sub SP. Okay. Now what do we know?
We know the compression is 1.2 millimeters when he's half the weight. Right?
Okay, so compression is 1.2 millimeters. What can we call that?
Delta X.
Delta
Y. in
Y.
this case.
delta Y equals, now I don't want to write down 1.2 millimeters. I want to write down in meters,
So 0.012.
0.012.
Yeah.
Yeah. 0.
Because the decimal moves 3 places, so it's 0.012 meters. Now, this is a delta Y. Is that positive or negative?
That's gonna be negative.
This is Y initial here, and this is Y final, right, after he compresses. So he started here and he went this way. Y final minus Y initial, that's a negative.
then we know that,
His weight.
yeah,
His weight is what?
9.8 times 70 kilos.
70 kilograms, 9.8 meters per second squared. What do we got?
a little over.
Little under 700.
668.
We're just guessing.
No,
6 something.
686.
Okay. 686 newtons. And what are we looking for A?
Constant K.
K. Okay. And then in B, we're looking for like a delta Y again, but it's when he's running. So it's going to be different. So we'll leave that alone for now. What should I do?
Do that little equation thing.
The little equation thing, like you mean some of the forces in the Y direction?
Yeah.
Okay. Because he's not doing anything right now. He's just rocked back on his heels. So he's just standing there. Some of the forces in the Y direction would be
So
what?
Speed.
It's going to be force of the spring minus half the weight is equal to.
Equals 0. He's just standing there. So the force of the spring
Is equal to half his weight.
And then we can do the force of the spring in the y direction equals negative k.
So 1/2 mg we should probably do, shouldn't we?
Well, 1/2 mg, though, we already calculated that, is 1/2 times 686.
That's 343.
343 newtons.
Yep.
Okay. Now we should be able to calculate K now, right?
Yeah, we know everything.
Yeah. So the force of the spring would be K times delta Y.
So we're going to divide by delta y.
But it's negative K, right?
Okay, good question.
In the y direction, Hooke's law is F sub P sub Y equals negative K delta Y.
All right. So the applied force would be down.
Yeah.
So our spring force is up,
It's going to be positive.
right? But we calculated our delta Y to be negative.
So k is not negative. It's just delta y is negative, right?
K is not negative. Delta Y is negative. So our K value is going to wind up being positive, right? The K itself is positive. The negative sign is just telling us that we're going the opposite direction. Okay, so
We don't have to put a negative sign.
do we or don't we?
Yes.
The delta Y right here is negative. We want the K to end up being positive.
So if you multiply a negative by a negative, you get a positive.
So this negative sign right here is going to give me the positive number that I want. So I want to solve for K. So I'm going to divide by delta Y. I'm actually going to divide by negative delta Y. So I have F sub SP over negative delta Y equals K. So I have 343 divided by negative, and then negative 0.0012 meters. So we get a positive answer. What is it?
Yeah, it's gonna be
285,833.
So what is it? 2,
285,833.
8, 3.
no decimals.
That I can see of
And this should be newtons, right?
0.333.
Per meter.
Newtons.
Yeah.
I'm really squeezing that in there. Newtons per meter. Okay. So that's our spring constant. Were you using a calculator answer the whole time, or is this a rounded answer? 686 is rounded?
No, it's not.
It's not?
686 was exact.
See,
Exact,
because
okay.
when you multiply 70 times
Right.
a decimal. it's
Okay,
gonna
just
go-
making sure. Okay, so now we want to find out how much the springs compress during the heel strike. How do we do that?
Well,
So then we know the K force, and then we just solve for the spring force, right?
So we know K now, how much
We
the
know
spring's
spring
compressed
force.
during the heel strike. So now he's hitting, as he's running with one heel at a time, right? So
we have-
his full weight hits the ground, one heel at a time.
And it's 5 times.
So it's going to be 343 times 5.
It tells us with a force 5 times his weight. So we have 5.0 times his weight, which is mg, or we could just say W, right?
Yeah.
Okay, equals
No, 1/2 W. Remember, because
No, because he's on
his
one
whole
foot at a
weight
time.
is on one heel.
oh,
Before it was both of his feet were
Yeah,
down and
okay.
he was rocking back, so that's why we just took half his weight.
Is equal
Okay,
to
equals what?
K times delta Y.
K times delta Y.
And we know K is that.
So it's actually
negative K.
negative K times delta Y.
And we can divide by negative K. Right?
We can divide by negative K to find the delta Y.
But delta Y should end up negative.
And I don't want to use, okay, we can use weight. That's fine. Never mind. So I can divide by negative K. This delta Y is different than the other delta Y that we were using. Okay?
Okay.
So we have 5.0 times W, which we know,
686.
divided by
The 28583. Oh yeah, negative.
newtons per meter. The newtons are gone. The per meter in the bottom becomes meters on top. And we wind up with a delta Y of whatever it winds up being. What is it?
Negative 0.012. So it's literally the same thing.
No, it's not.
Oh.
This is meters.
That's 12 centimeters, right?
That's negative 12, 1.2, not 12 centimeters. You would not compress 12 centimeters in your running shoe, right? But 1.2 centimeters in your shoe is pretty significant.
Yeah, you're right.
So that spring is actually doing quite a bit of work in your shoe. It actually does do something. It's not just a gimmick.
Aren't those shoes like banned in some places?
I don't know.
Do like
They actually do something. It's not a gimmick, right? They actually do something.
or just stick flubber on the bottom of your shoe.
What's flubber?
Ever
Flubber.
seen flubber?
That's with a famous actor who played Genie in Aladdin. I can't remember his name.
Okay.
No, it's not.
Spring is attached to a hook.
Not
Totally irrelevant. Ignore it.
Robin Williams.
2.0 kilogram hook. Just stop. The other end of the spring is pulled by a motorized toy train that moves forward at 5 centimeters per second. The spring constant is 50 newtons per meter, and the coefficient of static friction between the block and the surface is 0.6. The spring is at its equilibrium length at t equals 0 seconds when the train starts to move. When does the block slip? So what's happening here is the train is pulling forward at 5 centimeters per second. The block is stationary. The spring is stretching, which is going to apply more and more and more force to the 2 kilogram block that's just sitting there. Eventually, the force will get so great that the block will break free.
But then it's going to go the whole compression.
Well, yeah, but that's not the point of the problem, right? The question is, when does the block slip? So we need to figure out the breaking point of the block, right? The maximum static friction force that the block can withstand
So F.
So we need to find.
is what we kind of need to figure out, right?
So why don't we do some of the forces in the X direction?
Oh,
Would it be
some
good?
forces.
I figured that would be pretty helpful.
Yeah? This is actually an easier problem than you think. Some of the forces in the X direction or some of the forces in the Y direction or both?
X direction. There's enough so.
How about both? Because the normal force is going to dictate.
The static friction.
Yeah.
Oh yeah.
So we're going to need some of the forces in the Y direction and some of the forces in the X direction. but you guys are a little bit ahead of yourselves. We should probably draw a free body diagram for what?
The block.
The block. So here's my block. What is acting on the block?
You're gonna have
Spring
weight down.
force in the X direction.
Okay.
Right.
We have spring force to the right.
You're gonna have static friction to the left.
We're going to have the friction force to the left. So F sub S.
Up we have
You're gonna have
normal
weight
force.
down.
We have normal and weight.
Wow. We have everything. It's like a compass.
Kinda.
North,
Northwest.
west.
Yep. We got them all. Okay, so now some of the forces in the y direction. What do we got?
Negative weight
So normal minus weight.
is equal to 0.
Yeah.
So we're just gonna have normal equals weight.
Okay. Now some of the forces in the x direction.
You're gonna have
Force of the spring minus.
minus the static friction.
Equals.
0.
Yep. We're not moving yet. Okay. So now we know that the force of the spring
Is equal.
equals the static friction force. But now the force of the spring can be written as what?
K
Negative
times
K
delta.
delta Y.
The
It'd be
force-
positive K.
The force of the spring would be K delta X.
Oh,
What about the static friction force?
Mu sub S times N.
The maximum static friction force would be mu sub S times the normal force. But up here we know that the normal force is equal to the weight, right?
Yeah.
So therefore, instead of writing mu sub S N, I can write mu sub S W, but W is
FG.
mg. So from the sum of the forces in the y direction and the sum of the forces in the x direction, I just put together a really good equation here.
And we divide by.
And what is it that I'm looking for?
Mu sub
mu
S.
sub S, and we divide by mg.
I'm looking for mu sub S.
What?
I'm given mu sub S.
You would be looking
Oh, yeah.
for
Oh, delta S. No.
When the train, when does the block slip is what we're looking for.
a delta T.
I actually need a delta T, but there is no delta T in this equation. However, I can find delta X. And once I find delta X, I know that the train is moving forward at 5 centimeters per second. I can use delta X to
Or,
find
you know,
delta
point
T. Okay?
0.005 meters a second.
So we can solve for everything. Well,
Divide by
K.
divide by this K. Delta X equals mu sub S mg divided by K. So I know all of this. Mu sub S is what?
6.6.
0.6.
M, the mass of the block.
2.0 kg.
And then G,
9.8 meters a second squared.
K,
Divided by 50 Newton meters.
50 newtons
Divided by
per meter. Okay, kilograms meters per second squared is newtons. Divided by newtons is gone.
So you're left.
Per meters in the bottom is all that's left, but that flips and becomes meters on top. So my units are good. Delta X equals, what is it?
Working on it.
I got around 10 times 2 is 20.
0.2352.
What is it?
0.2352.
Okay. 0.235 is what I'll write. What is that? Meters?
Yeah.
Okay.
and then
What is this number?
just centimeters.
Is that
That's delta X. That's how far the train moves before the block
before the
slips.
Okay.
Right? So now what?
23 centimeters.
That's 23 centimeters, yeah. The train is moving forward at 5 centimeters per second, so it would be smart to turn that into 23.5 centimeters because we're told it's 5 centimeters per second. Now, we basically can just use distance equals rate times time,
Yeah.
okay?
So,
So distance equals rate times time. Solve for time. Divided by r. Time equals distance divided by rate. So that would be
23.5 centimeters divided by 5.
Maybe that's with.
Oh my god.
4.7 centimeters per second.
not centimeters per second. The centimeters divided out. We're left with in the bottom per seconds, which flips to just seconds. 4.7 seconds before it breaks free.
That's pretty cool.
Okay? So really not that hard of a problem. Drawing the free body diagram definitely helps. Some of the forces in the y and some of the forces in the x, because we needed the y direction to get the static friction to flip over to normal, to flip over to mg, so we could substitute in. Okay? All right, one more thing. A 1 kilogram weight is suspended from a spring, stretching it by 5 centimeters. How much does the spring stretch if the 1 kilogram weight is replaced by a 3 kilogram weight? You got it? What is it? C? Yep. Why? Why is it C in your head?
Proportional.
3 times 5 is 15.
Proportion. Yep. We got 1 kilogram over 5. We're going to turn that into 3 kilograms over X.
Cross multiply.
Cross multiply. 1X equals 15. So there you go. Pretty straightforward. Proportional relationships, you can set up a proportion to solve it.